section 2.1 entitled Functions. In this section we'll talk about functions, relations, functions, evaluating functions, and even how to find the domain of functions. And additionally, we'll talk about how to tell whether a relation is a function or isn't a function. So to begin, a relation, before we talk about functions, we need to talk about relations. Relations are correspondences between two sets, and we could express relations any of four ways. We could represent them as a equation, as a graph, as ordered pairs, or by a mapping diagram. A relation maps input values to output values. The input values are commonly known as the domain of the relation, and the outputs are commonly known as the range of the relation. A function is a special type of relation that maps each element of its domain with a unique element in its range, in which any element in its domain only has one corresponding element in the range. So you can see all these elements here in the domain pair exactly to one element of the range. All right, every function. It's important to know that every function is a relation, but not every relation is a function. So if we had this x value here going to this y value here, in addition to going to this, mapping to this y value, this would not be a relation. But the relation that's shown here is a function. All right. Functions are often denoted by letters such as a scripted F, capital italicized F, scripted G, or uppercase italicized G. We write a function as f and then x in parentheses, and it's read as the function f evaluated at x. It is not read as f times x. I thought that when I was in high school taking Algebra 2, but that's not the case. And the value x is a element of the domain of the function. You can think of a function as a machine. It only accepts numbers from the domain of the function, and then for each input there is exactly one output. And as we saw before, that output might be repeated for different inputs. So basically you pick a value x that's in the domain of the function, you put it into the function, and you do perform some operations, and you get an output value. All right. For a function y equals f of x, the variable x is called the independent variable, and the variable y is called the dependent variable. The independent variable can also be called the argument of the function. So our first example here, if g of x equals x squared plus 8x minus 24, we're going to find each value. We're going to find the value of g evaluated at 6 first. Let me pick a different color here so we can see it. Alright, so the function g evaluated at 6 here. Alright, g of 6 equals, what we're going to do, we're going to take the value of 6, and wherever we see an x, we're going to replace it with an x. So g of 6 equals 6 squared plus 8 times 6 minus 24. 6 squared is 36. 8 times 6 is 48. And subtract 24. And then in a basic calculator, you could evaluate that all at once. 36 plus 48 minus 24 equals 60. So the function g evaluated at 6 is 60. All right. Next example is going to look a little different. Let's find g of negative 4x. We're going to use the same exact function as before, except now we're evaluating the function g at some value of x, and specifically negative 4x. So wherever we see an x, we replace it with a negative 4x. So we have negative 4x squared plus 8 times negative 4x minus 24. Now when we're evaluating a function at another variable, we're going to get an expression in terms of another variable. In this case, we're going to get an expression in terms of x. Negative 4x squared, if you use your properties of exponents here, this is going to be negative 4 squared. We square each term here in the parentheses, times x squared, plus 8 times negative 4x is going to be negative 32x minus 24. Negative 4 squared is 16 x squared, plus a negative. We could clean that up by writing minus 32x and then minus 24. So the function g evaluated at negative 4x is 16x squared minus 32x minus 24. So let me write that. G of negative 4x equals 16x squared minus 32x minus 24. And then the last one, evaluated at the function g at 5x plus 4. So wherever we see an x, we'll replace it with a 5x plus 4. So we have 5x plus 4 quantity squared, because we're not just squaring the 5x or the 4, we're squaring all of it because we're replacing this x with 5x plus 4 plus 8 times 5x plus 4 and subtracting 24. So here we get 5x plus 4 squared. That's a perfect square trinomial. So we'll get 25x squared. 5x times 4 is 20. We add it to itself. We get plus 40x. And then 4 squared is 16. Distribute this 8 to the 5x and the 4. And we get plus 40x plus 32, and then subtract 24. And now it turns into combining like terms. Do we have any like terms with 25x squared? We do not, so that stays as a 25x squared. Do we have any terms that are like with 40x? Well, yes, we do. 40x plus 40x. That's going to be plus 80x, and then everything else are constants, are 16 plus 32 minus 24. 16 plus 32 minus 24 is 24, so we get 25x squared plus 80x plus 24, and that is the function g evaluated at 5x plus 4. Okay, so that's how to evaluate a function. Let's move on and talk about how to find the domains of functions. All right. Sometimes the domain of a function f is not specified if only an equation is given. In those situations, the domain is considered to be the largest set of real numbers for which the value of f of x is also a real number. 3 steps to finding the domain of a function. You start with the domain as the set of real numbers. Sometimes in this class and before, you probably have seen the real numbers represented like that as a bold-faced R. That also means the set of real numbers, mathematically speaking. So if we say the domain is all real numbers, that's sufficient enough to put instead of writing out all real numbers. So that's the first step. Start with the domain as the set of real numbers. If the equation has a denominator, exclude any numbers that give a 0 denominator. And the third step is, if the equation has a radical of even index, exclude any numbers that cause the expression inside the radical to be negative. So in essence, we start with the set domain as the set of real numbers, and you have to figure out if you can create a division by 0 or any imaginary numbers, what those numbers are, and then exclude them from the domain. All right. If the value of x is in the domain of a function, we say that f is defined at x, or the function f of x exists. And if x is not in the domain of a function, we say that the function f is undefined at x, or the function f of x does not exist. So number 2, second example here, let's find the domain of the following functions. We have 3 functions that we'll find the domain of, and then that will be the end of the video here for today. Let's find the domain of the following functions here. The first function is f of x equals x squared minus 3x. Remember, we start with the domain as the set of real numbers, right? Start with the real numbers. All right, and we have to figure out, can we create a division by 0 here? Well, no, we can't create a division by 0 here unless we introduce something. So, so in this problem specifically, there's no division by 0. And secondly, think of a radical of even index. Do we have a radical of an even index here? No, we don't. So we won't create any imaginary numbers. Right, so if we can't introduce a division by 0 or can't create any imaginary numbers, then this function, its domain, is simply the set of all real numbers. With most of these types of functions that are quadratic, the domain will always be the set of real numbers. All right. Second example here, the function g of x equals 2 plus x divided by x squared minus 7x. All right. Remember, start with the domain as a set of real numbers and figure out, well, can we create a division by 0 or can we create imaginary numbers? What I noticed, this function here, g of x equals 2 plus x over x squared minus 7, it has a denominator. And remember, we cannot create a division by 0 here, so we have to figure out what values of x here would create a division by 0. And the way we do that is by solving equations. By solving that equation, x squared minus 7x equals 0. And there's many ways that you can solve a quadratic. You could use completing the square, you can use factoring, you could even use the quadratic formula. In this case, factoring is going to be the easiest because we can factor out a common x from both x squared and 7x and get x times x minus 7 equals 0. And then we can use the zero product property to say x equals 0 or x minus 7 equals 0. And solving x minus 7 equals 0, you get x to be 7. So these two values, 0 and 7, would create a division by 0. So our domain is a set of real numbers, but we can't have the values of 0 or 7. So x cannot be 0 or 7. We understand that the domain is a set of all real numbers, but we put these restrictions on it. Basically, when we say x cannot be 0 or 7, it means any other real number is in that domain. And then let's see, can we create any imaginary numbers here? No, we can't, because there's no radical of even index. All right, so there's your answer for 2b. And then 2c, find the domain of that function, h of x equals 1 over the square root of x squared minus 16. Well, first off, we need to, we could have a division by 0 here, so we have to set the square root of x squared minus 16 equal to 0, but more importantly, we also can create an imaginary number under here. So what we have to do is set x squared minus 16 greater than 0. All right? And we'll solve each of these two different equations, this equation first and this inequality second, and get an answer. So basically, to undo the square here, the square root, we square both sides, and we get x squared minus 16 equals 0. 0 squared is just 0. add 16 to both sides, and you get x squared equals 16. And take the square root of both sides, and you get x to be plus or minus 4. Whenever you introduce a square root like this to an equation, you always have to account for the positive and negative root, because yes, it's true that 4 squared is 16, but also negative 4 squared is 16. So here's our first restriction. Right? There's one restriction. Let's find our second restriction. X squared is greater than x squared minus 16 is greater than 0. So in this case, add 16 to both sides, we get x squared is greater than 0. And then take the square root of both sides, and you get x to be greater than, oh, that should be a 16. So let's change that right there, is greater than positive or negative 4. All right, so this is our second restriction. Okay, so if we look at this, all right, our values of x have to be greater than positive or negative 4, so x is either greater than negative 4 or x is greater than positive 4. Right? But we can't have the values of positive or negative 4. So our domain here, to clear it up, of this function, we're going to start with x is greater than negative 4, because that's pretty much the lowest value that we can have. Anything less than negative 4, including negative 4, will give us an imaginary number or produce a division by 0. So our domain is going to be x is greater than negative 4, with the stipulation, because x can't be negative 4 over here, right? From this first restriction, creating a division by 0. That tells us x can't be negative 4, but we run into the problem if x is greater than negative 4, we run into the problem where x is positive 4, which is one of our restrictions that we found here with the division by 0. So x is greater than negative 4, and x cannot be positive 4. So that takes care of this restriction. And by saying x is greater than negative 4, we also say that we take care of the part of the second restriction where x is greater than 4. So that's our domain of the last one, okay? Of the last example. All right. Thank you guys for watching. Have a wonderful day.